Hi, welcome back. In today's lecture, we're going to be talking about sets and constants. They can be declared within the B machines, and to ensure model proof, they're seen by their properties and not their values. The details of the sets and constants can be given either at declaration or later during refinement. In this lecture, we're going to be using a case study called the club. This is an abstract machine used to store information of some club members and those wishing to join the club. So suppose we have two groups of people, the members of the club and the waiting list. In this case, we may have one set called name that represents the type of potential members, and two constants, capacity, the maximum member capacity of the club, and total, which represents the maximum size of the set of names wishing to join the club. The clause set is used to introduce new types that can be used in the machine. However, types from different sets are incompatible. For example, in the following machine, you can't relate T0 and T1, the two sets that are declared in this machine, even if they represent interval of integers. The sets can either be enumerated sets or deferred sets. In the declaration of enumerated sets, we explicitly list the elements of the set. In our example, we can have a set called report with two elements, yes and no. Notice that the elements of enumerated sets can't be replicated from one set to another and can't be defined with constant values. The deferred sets, however, are finite and not empty. They're only valued by interval of integers, but their values are hidden in specification to enable strong typing. Their values are revealed in the implementation. In our example, we could have another set, a deferred set called name, to represent the set that contains all the names of club members. In our example, then, we'd have two sets, the set report, which is an enumerated set, and the set name, which is a deferred set. The clause constants lists the constants that can be used in the machine. The constants can have any type known to the machine. For example, natural numbers, power sets, Cartesian products, they're all valid constant types. In our example, we could have two constants. The constant capacity that represents the maximum number of members in the club, and the constant total that represents the maximum number of people in the waiting set. The constants keyword is a shortcut for concrete constants. The concrete constants are constants that are directly implementable, like for example scalar values, and they do not require further refinement, but they require valuation in the implementation. On the other hand, the abstract constants are constants that will be refined, and they can't be defined in the implementation. The conditions that are satisfied by the constants and the sets are declared in the clause properties. The machine must be able to fulfill these properties. In our example, we could have the clause properties declaring that the capacity and the total are both natural numbers greater than 0, but also could declare that the cardinality of the set name is greater than the capacity, and that the total is also greater than the capacity. Regarding visibility, given an abstract machine with sets and constants and variables, we have that the clause properties of this machine is able to read the sets and the constants, and the invariant of this machine is able to see the sets and constants and also the variables of the machine. The assertions of this machine is also able to see the sets, constants, and variables of this machine, as the initialization of this machine and the operations of this machine, which are also both able to see the sets, constants, and variables of the machine. So, let's now go back to our example, the club machine. Our club machine is named club, and we have, as we saw, two sets, the report with two elements, yes and no, and a deferred set called name. We also have three constants, the total, the capacity, and a constant that represents the maximal number of names. We declare in the properties clause that the capacity is a natural number greater than 0, but it's less or equal than 100. We also declare that the cardinality of the set name is greater than the capacity. The total is also a natural number greater than 0, but it's also greater than the capacity. Finally, we have that the constant max name is a natural number also greater than 0, and its cardinality, the cardinality of the set name, is equal to the max name constant plus 1. In this machine we have two variables, the variable member and the variable waiting. The member stores the names of the members of the club, so it is declared the invariant as a subset of name. The waiting represents the names of the people that are waiting to join the club, so it's also a subset of name. Of course, one person cannot be a member and also be sitting in the waiting list, so the intersection between these two sets is empty. Finally, we have that the cardinality of member is less or equal than the capacity, and that the cardinality of waiting is less or equal than total. Both sets, the member set and the waiting set, are initialized with with the empty set. So, our machine has 4 operations. One operation to someone join the club, to someone join the queue, the waiting list, to remove someone from the club, and to query if someone is a member of the club. The join operation receives a name of someone that is in the waiting list. So in the precondition we have that NN belongs to waiting. But we also need to have empty places in the club. So the cardinality of member must be less than the capacity. If this precondition is satisfied, then we include the given name to the set of members and take that name out of the set of waiting people. The second operation, join queue, includes someone in the waiting list. So it receives a name, but this name cannot be a member and also cannot be already in the waiting list. But the cardinality of the waiting set must be less than the total, so we need to have 3 places in the waiting list. So, if that precondition is satisfied, we include that name to the set waiting. The third operation, remove, receives a name of a member. So it receives a name, but that name must be a member of the member set. And what we do, we simply take that name out of the member set. Finally, we have the query operation, the query membership operation, that gives an answer as output. So it receives a name, and if that name belongs to member, the answer is yes. So it says yes, that given name is a name of a member of the club. But if the NN is not a member, a member of the set member, then the answer is no. So that concludes the specification of our machine. As we can see, there are some proof obligations that are left unproved by the automatic theorem prover of Atelier B. And all those 4 proof operations are related to well-definedness properties. Basically, we need to prove that the set name is a finite set, and that's because we use the set name as a parameter, as an argument given to the function card that gives the cardinality of a finite set. So for that reason, we need to include in the properties of the set that it is indeed a finite set. And the same happens to member and to waiting. And once we include these predicates to the invariant and to the properties, we have that everything is automatically proved and then that our abstract machine is indeed consistent. We can now animate the club machine in Pro-B. So when you load that machine, let's say we set the constant total to be 5, the capacity to be 1, and the maximum name to be 9. We initialize both sets with the empty, and we can now either join someone to the queue or query for the membership. Notice that any query will result in a null, because we have no members basically in the club, and all we can do is to make people join the waiting list. Let's join name 5, and now that guy, only that guy, name 5, can join the club. Let's also join name 10 and name 3, so that these 3 guys can join the club. So we can have name 5 join the club, and now as we reached our capacity of the club, which is just 1, no one can join the club. Only if we remove name 5 from the club, now again name 3 and name 10 can join the club. And of course, we can have a random animation, let's say, of 100 random operations, and we see that we still have our straight properties satisfied. Of course, this does not prove that the machine is consistent. We have done so using Atelier B, but that gives us a good hint that the machine may indeed be consistent. We should now discuss about machine consistency, given that we have the properties clause. The first thing we have to prove is the feasibility of the properties. Basically, there must be values for the sets and the constants that satisfy the established properties. So for example, let's suppose we have the sets st, the constants k, and the properties b. We have to prove that there exists values for st and k that satisfies the properties b. In our example, we have to prove that there exists name, report, total, and capacity such that the kernel of name is greater than the capacity, the total is greater than the natural one, and the total is greater than the capacity. Atelier B generates these proof obligations only at the implementation constants consistency check. If this proof obligation is not satisfied at the machine, we will not be able to implement this machine because it contains a miracle. Let's take as an example this miracle machine, in which we declare a constant kk with a property that says that it's a natural number, but it is less than 10 and at the same time is greater than 10. Of course, we will not be able to fulfill this property. However, to generate code, we will need to provide an implementation of such machine. So let's suppose we provide the miracle I implementation, which says that the value kk is 2. Of course, we will not be able to implement the machine miracle, and this is highlighted here in Atelier B by giving that one proof obligation was not automatically proved, and if you check, we're actually trying to prove that 2 is greater than 10, which is part of the property we just declared. In that sense, we simply not be able to implement the miracle machine. So if we have such a problem in our project, one possible scenario is that we have an abstract machine like our miracle machine, and which has unfeasible properties, but we base our further development on that miracle machine, and we provide machines that see that miracle, and then we implement these machines. The problem is that at some point we have to implement the miracle machine, and as we saw, we will simply not be able to implement that machine, and that will cause the whole project to break the whole project, because we are based on a miracle machine, on a machine that we are not able to implement. There are two good ways to ensure the properties of the sets and constants before we have that problem. The first one is to use the assertions clause in a specific separated machine. And the other one is to implement the machines that contain the properties clause before we move on. In the miracle example, if we decide to use the assertions clause, we could have a machine called miracle consistency that has just one assertion that says that there exists a KK such that the property holds. As we can see, atelier B will not be able to prove that predicate because, as we know, the predicate there exists KK such that the property we described holds is not feasible. If we decide to go using the second way of implementing machines containing the properties clause before we move on, we could have simply tried to implement the miracle machine, and as we saw, the problem would also be shown. However, we could also use a separate context machine to make the sets and constants visible to other machines. So we could have a machine miracle that sees another machine. So by using the sees clause, as we see in a lecture later on in this course, the miracle 2 machine, we have access to the sets and constants declared in this machine. In our example, we have that the miracle context machine has a constant KK with the properties we just described. We could then simply try to implement this context machine, and the same problem as we saw before would be shown. So we will not be able to prove the consistency of this machine because, of course, 2 is not greater than 10. In our example, if we decide to use the assertions clause, we would have the club machine, as we just saw, but then we would have to define a club consistency machine with the assertions in the format we just described. We would have then to prove that the club consistency machine is consistent, and only then would be allowed to implement the club I to make further developments. If we move into atelier B, we can have the club consistency machine saying that with an assertion that says that there exists name, total, capacity, and max name such that the whole predicate holds. As we can see, atelier B was already able to automatically prove that assertion, which means that we have that the club consistency machine is consistent and that our properties are feasible. In our example, we could already have directly implemented the club machine by providing an implementation of the club machine, like, for example, club I. But we could do that possibly using context machine as we saw for the miracle machine. So we'd have a club 2 machine that sees a club 2 context machine. And then before trying to implement the club 2 machine, we could first only provide an implementation of the club 2 context machine, and then we would be able to further develop the club 2 machine. Looking in atelier B, our club 2 machine would see the context machine, and this context machine would only contain the sets and the constants and their properties. The first thing we'd have to do is to provide an implementation of that machine. So our implementation refines the context machine and has to provide values for all the sets and constants that were not already valued. So for example, max name would have value 10, name would be the set of numbers ranging from 0 to max name, total would be 10, and capacity would be 5. As we see, atelier B was already able to prove the consistency of the machine, of the implementation. Finally, would be able to provide an implementation for that club 2 machine. So once we have proven the property's feasibility, we can then move to the invariant consistency. In the previous chapters, we have seen that the invariant consistency was simply proving that there exists a value for the state variables of the machine that satisfy the invariant. But now this invariant may refer to the properties clause. We are then able to include in the left-hand side of the implication the properties clause that will be very useful to prove that there exist values such that the invariant holds. In our example, we'd have that the properties clause that we had, the capacity is a natural number greater than 0, names a finite set of names, the cardinality of name is greater than the capacity, and the total is also a natural number greater than 0, and the total is greater than the capacity. That would be our property. The left-hand side of the predicate that says that there exists member and weighting such that the invariant holds. You can prove that such values exist simply by providing the empty set by valuing the member and the weighting variables with the empty set. As we can see, of course, the empty set is a subset of name. The intersection between two empty sets is an empty set, and as capacity is a natural number greater than 0 and total is a natural number greater than 0, they're both greater or equal than the cardinality of the empty set, which, as we know, is 0. And that finishes the proof of the invariant consistency of our example. The next predicate we have to prove is the initialization consistency. We had before that we had to prove that the precondition, the weakest precondition for the initialization T to establish the invariant I was true. But now, as we had for the invariant consistency predicate, we also have that the properties hold. So the properties will be in the left-hand side of the implication. In our example, we have to prove that the properties, as we saw before, implies that the initialization establishes the invariant. So we have to prove that the initialization, which makes member receive the empty set and weighting receive the empty set, establishes the invariant. So by simply replacing member with the empty set and weighting with the empty set, we have exactly the same predicate as we had before for the initialization consistency, or for the invariant consistency. So, as we know, that predicate is also true. Finally, we have to prove that the operations of the machine are consistent. As we have seen before, for the operations we have to prove that once the invariant and the precondition holds, then the command has to establish the invariant. As for the initialization consistent predicates, we also have now, in the left-hand side, the properties. So we have to prove that given that the properties hold, the invariant holds, and that the precondition holds, then we have that the command establishes the invariant. In our example, for the join operation, we have that the properties and the invariant and the precondition are this big predicate here, in which we have the properties, the invariant, and the precondition. Now we have to prove that this big predicate implies that the substitution of the join operation establishes the invariant. So by replacing member with member union NN and replacing weight with weighting minus NN, we have this predicate here. Now that we have this big predicate here, we can actually take a look and see how we can prove that this predicate is true, this implication is true. First, we know in the left-hand side that member is a subset of name, and that NN is a name. Then we have, of course, that the union of member with the set that contains NN is a subset of name. Next, we have in the left-hand side that weighting is a subset of name. Then, of course, by removing n set, n member of weighting, like NN, will give us still a subset of name. Next, we have in the left-hand side that member intersection weighting is the empty set. And given this, we know that by removing n element of weighting and putting it into member will give us still an empty intersection. Next, we know in the left-hand side that the cardinal of member is less than capacity. Then, of course, by including one element in that set, will give us a set whose cardinality is less or equal than capacity. Finally, we have that the cardinal of weighting is less or equal than total. Then of course, by removing any element of weighting, will still give us a set with a cardinality less or equal than total. And that's finished the consistency proof of our club machine. So in summary, to prove the machine consistency, we have to prove 4 properties. First, that there exist values of St, the sets, and the constants k, such that the property holds. Then we have to prove that if the property holds, then there exist values for the state variables that satisfies the invariant. The third one is related to the initialization. We have to prove that if the property holds, then the initialization common t will establish the invariant. Finally, for each operation of the machine, we have to prove that given that the property holds, the invariant holds, and that the precondition holds, then the operation command S establishes the invariant. So, that's all for today's lecture. I hope you enjoyed it. See you in the next one. Bye.